Hello there, my name is Kevin Schultz. I teach physics at Hartwick College, and I'm here today to give a little presentation about a really exciting new telescope that's going to be launched into space. I think the last I saw was this December. It keeps getting pushed back, but as we'll see, it's a very complicated, very cool spacecraft. And so we want to make sure that everything is just right, because once it leaves Earth, we're not going to be able to fix it like we were able to fix the Hubble Space Telescope. So we got here a picture on your screen of what the James Webb Space Telescope is going to look like when it's all done. And we'll talk a little bit more about that in just a moment. But first of all, I want you guys to look at a few different pictures that we have here. So this picture here, you can see is split down the middle. And this is of a galaxy that can be found in the Big Dipper. And we can see on the left-hand side here, it looks like kind of the familiar sorts of colors that we might expect to see. We see a bunch of big stars and this blue fuzz over here. This is, that is gas that's just sort of being it's glowing because there's so much energy from the stars that are there. And then over here on the right-hand side, it looks like it could be part of it. So you can see this arm is spiraling out like this, and maybe this arm as well, but it looks a little bit different. So let's go on and see what else we have. So this, believe it or not, is two pictures from the same part of the sky. It's a little bit bigger. You can see it's a little bit not quite the same. So we have this deep, beautiful red star here and a little orangey one right next to it. And that's these two stars over here. So we can see that it's not quite the same. But it doesn't take a very fancy scientist to be able to tell that this is probably the same picture, but there's something is going on in the background over here. In this region, and this picture here on the left, we can't see anything. That's because the stars that are behind this cloud are being obscured by this cloud, and it's scattering all the light out. But over here, when we look at it in a different set of colors, we see something a little bit different. And so we can do that right here on Earth as well. I'm going to switch cameras. And there you go. Let's make me look a little bit bigger over here so that we can, I should be able to pin myself. There we go. There we go. Nice and bright. So here what I got is I got a nice a really cool thermal camera. And so this is looking in what we're going to call as the infrared. And we'll talk about what this means in a little bit, but it's very different. So here I've got a piece of plastic. And when I hide behind it, you can't see me as well. The camera shows a little bit of, there we go. See, peeking through there on the other side. If I switch to my regular camera, there we go. This piece of plexiglass doesn't make much of a difference whatsoever. But if I switch again to my infrared camera, you can't see me. This material here blocks infrared. Now, I can have something as well, and don't try this at home because this is not very safe. But I could hide myself in this little plastic bag here and you can't really see me. But if I switch my camera, and I'm looking really silly right now, all of a sudden you can see that this material lets the infrared light all the way through. And so maybe you can't see me as well, but you can tell that there's somebody there. And so this is one of the big reasons that we look at different colors when we are looking at the sun. I mean, we're looking at telescopes. So let's go back to this. Right there. Oh, there we go. That's what we want. And that's what's happening. So on the left here, we're looking in what we call the visible light, and the gas that's here, this ink cloud, this black cloud is absorbing all that visible light, but it is what we say it's transparent to infrared light, just like the various pieces of plastic that I was hiding behind were transparent to some colors, but not to others. Here's another picture. So here is a familiar constellation of Orion, which should be rising at more reasonable hours now that we're getting into the wintertime. So you might recognize Orion's belt over here, and then the sword of Orion, and then this little fuzzy spot right down here is Orion's Nebula. The cool thing is that this winter, when you get a nice clear night, even though it's a little bit cold out there, go out there because the wintertime is the best time to look at stars. And if you follow Orion's belt and you look for his sword and you're not too bright lights in the city of Oneonta, you'll be able to see a very, very faint splotch of almost like it looks just almost like a fuzz from a Q-tip or something like that. You can barely just see it. You almost might not even believe that you're seeing it, but you can. And that is Orion's Nebula. And that is a birthplace. That's where stars are being born right now. And if we look at the right-hand side of this picture, we see the same constellation of Orion, but we're seeing it in infrared. And it looks very different. Space looks very, very different depending on when you're looking at it in the visible light, the light that our eyes can see, or if we are looking at the infrared. And again, one more picture looking at the difference between visible and the infrared. And so we notice, what we notice are the things that I've already shown you, which is that we can learn different things about space. We can learn different things about what's going on around us by looking at different colors. That there is a lot more to the universe than just the little bit of color of light that we can actually see with our eyes. And so the James Webb Space Telescope is the newest of these telescopes that allows us to see in the infrared. Clearly, we've got some pictures here from other space telescopes. These are mainly from the Spitzer Space Telescope in infrared, and the visible in the visible light, it's the Hubble telescope. The James Webb Telescope will allow us to see a lot new things. The other thing that we can find out is that we will have that there are other telescopes that look at X-rays, and there are telescopes that look in the ultraviolet and all sorts of things like that, but and sometimes even in the radio waves. We are going to be focusing today just on the infrared and a little bit of the visible, because those are the things that the James Webb Space Telescope is going to be looking at. So if we want to understand this, we have to understand a little bit about what light is. Maybe you've seen this in a science class, maybe you haven't yet, depending on what grade you're in. But light is made up of electric force going up and down, up and down, up and down, up and down, and a magnetic force going side to side, or maybe it's going like this and going like this. And they are at right angles to one another. So the electric field is here in blue, it's going up and down, and we see that the magnetic field is going side to side. And it's really hard to do this at the same time. Oops. Well, I never get it right. And it propagates along here. And these electric fields, these magnetic fields, act on different materials. They cause us to have reflections, and so what we all get to see. But for us, the key thing that makes the light different, different colors of light, is what we call the wavelength. So you probably saw this in a math class, right? It's the distance between from the trough to the trough, or the crest to the crest, or something else that you thought might not really have been all that important. But the only thing that makes different colors of light different from one another is just this wavelength. And those colors that have longer wavelengths are in the radio waves, and then we can go up to the AM radio in your car, or FM radio in your car, and those get smaller and smaller and smaller at wavelengths and become more and more energetic. And then we get to our microwave. Our microwave oven works basically by a special kind of light that has a wavelength that's actually about that big. It's about 3 centimeters long. If you want to find out exactly how to do this, and you don't mind cleaning out your microwave oven, you can put in little pieces of chocolate all along there, turn that oven on without the rotating thing, and measure the distance between the melted pieces of chocolate, and they'll tell you the wavelength of your light. Like I said, I would talk to your parents, or at least be willing to clean that up after you do that experiment. As we go along through here, we go from microwave to the infrared. This is where James Webb Telescope is going to be located at. And then here is the visible light. Here's our Roy G. Biv in reverse, R-O-I-G-B-I-V. And that goes from 750 nanometers, or 750 billionths of a meter, right? So that's pretty small, all the way out to even the smaller 380 billionths of a meter. And just this small little slice of the spectrum is what our eyes are looking at. And so this tells us right away that we must be missing a lot, right? And so this is what we saw in some of those pictures. And so as we're going forward and we get further and more energetic, we have ultraviolet light, and then X-rays, and then gamma rays. And these X-rays and these gamma rays are so powerful that it's really, really hard to actually capture the light and focus it down. So you have to do these really, really special tricks with having the mirrors, instead of the light coming in bouncing like this, you kind of skim them off the mirrors just a little bit. And it's a much more difficult thing to do. And so this is the spectrum of light. And like I said, the only thing that makes a difference between these is the wavelength, or the distance from a peak to peak in the spectrum. I mean, from the electric waves. To give you an idea of what kind of size we're talking about with these infrared, also we were talking about the visible light is a couple hundred billionths of a meter, so that's pretty small. The wavelength, the word that we use for infrared are called microns, so millionths of a meter. And to give you an idea of what kind of things that we're looking at, your cell phones, or your parents' cell phone, or whatever, are operating at wavelengths of 160,000 microns. Your microwave oven, like I said, is at 3,700 microns. The longest wavelength of light that Webb is going to be looking at is 28 microns. And I don't know about you, but these numbers really don't mean a whole lot to me. And so I've also included here a couple of little things here that might be a little bit easier to understand. So at the longest wavelength that Webb is going to be able to look at is 28 microns. If we look here on our chart, we see that that's a wavelength that is about the size of a piece of pollen from grass. If we're looking again at our microwaves, that's much bigger than even an amoeba or something like that. I mean, much smaller than, microwave is much bigger than even an amoeba. So by looking at these different things, we can learn different bits. And so again, here we have our a thermographic image of a lemur, just like when we were looking at me being kind of silly with the infrared camera. Depending on the temperature of the different parts of my face, we are looking at my heat signature, because everything glows that is at a particular temperature. And the hotter you are, the shorter the wavelength that you glow in. Now, humans are at 98 degrees Fahrenheit, and so we're going to emit light that is appropriate to that, which turns out to be infrared. So that's always a little scary to look at yourself in infrared. So let me go back to the regular camera over here. And so now, how is James Webb Telescope how is this going to help us? So remember what I just kind of said, that the hotter something is, the more it's going to glow. And so I'm going to switch again to a different share here, go over here to a website that is a really interesting website. They have a lot of different little tutorials, little kind of applets that you can run on various things about science. So it's called fet.colorado.edu. If you just Google PHET and physics or something like that, you'll be able to find right away the website. So we're looking here at their black body spectrum, and what that means is that it's a sciencey term that basically just says that if you're black bodies are objects that both absorb light perfectly for all wavelengths, and they emit them perfectly as well. And so it's a pretty convenient approximation to things. So what I've got here is I've got a little temperature knob here, and I'm going to go ahead and take a picture of this. And so the surface of the sun is about 5,900 Kelvin. What's a Kelvin? Well, it's basically like Celsius, which is, for our purposes, kind of like Fahrenheit. It's just hot. All right, so 5,900 Kelvin is really, really hot. And this curve here is telling us how much of the energy that the sun is sending out from its surface is being spread out via different colors of light. So the first thing that we see is that most of the light that the sun gives out is in the visible, and it's kind of in the green. And also the sun is putting out some ultraviolet light, and then out here it's putting out a bunch of infrared light and so on. Now I'm going to go ahead and I'm going to find a brighter star. So we're going to go to Sirius A, and we can see a couple of things that are happening here. Oops. That curve got a lot bigger, right? So this star, Sirius A, that is a lot hotter than our sun, is also, as this is saying, is putting out a lot more energy than our sun is, which makes sense. It's a hotter star, it's got more energy, so it's going to give off more energy. And notice that what's happened is not only is it giving off more energy, it is shifted the peak of that to the ultraviolet. So our sun puts out most of its light in visible wavelengths, and Sirius A is putting out most of its energy in the form of ultraviolet. So now I'm going to cool things off a little bit, and we'll go back to this scale. So here we are, now we're back to the sun. Now we're going to go to kind of that old-fashioned incandescent light bulb. And now we see a couple of things that are really interesting. Now it's cooler than the sun, but still hot, 3000 Kelvin. And we see that it's gotten smaller. So a light bulb does not put out nearly as much energy as the sun. So that makes sense. And we see that it's putting out most of its energy now in the infrared, and it only puts out a little bit of its energy in the visible light. And that's why people are working so hard to get rid of these kinds of light bulbs, like this one right over here. Right, so that's what I mean by an incandescent light bulb, kind of what you think is a regular kind of light bulb. And we're replacing those with compact fluorescents, and we're replacing those with LED lights, because when we take our energy out of the wall, right, our electricity, it'd be nice if we used all of that energy to brighten up our room, right? That's what that light is for. And what we find with the old-fashioned incandescent lights is that most of that energy is that we take from the wall and converting it is being used to be turned into infrared light. And so basically just goes to heating up our house very inefficiently, as opposed to letting us be able to read or see or cook or something like that. And so that's one of the reasons that we do that. And we can go, I'm going to take a little snapshot of that. And we could go even colder to, say, the Earth's temperature, which is about 300 Kelvin, or about 70 degrees Fahrenheit. And so now we got to zoom in a lot, and we got to zoom out a lot over here. And even then, there we go. The Earth is not really emitting any visible light. It reflects the visible light, but it's not actually emitting it. It's cold enough that that's all that's happening. And so this is the wavelength range that we humans also typically are glowing at, maybe a little bit further this way. And there are very exact mathematical relationships that allow us to understand how the temperature and how the wavelength are connected. And that is why I can say, oh yeah, I know the temperature of the sun is 5800 Kelvin. Nobody's sticking a thermometer in that sort of thing, right? But we can look at the spectrum of the sun, and we can use that to determine how much energy is being put out by the sun, and then figure out how hot the surface of the sun is. And so this is one of the things that James Webb will be able to do, right? It's going to be able to look at very cool things, not like sun-like objects, but very, very cool things, and figure out what their temperature is. Right? And so this becomes one of the toolboxes that we can have when we are studying using light. This is one of the reasons why, personally, my background is in optics and atomic physics. And light is just this phenomenal tool that we can use to be able to understand what's happening. And so I'm always a big fan. I think it's always the coolest thing ever. So that's one of the ways that we can use this, right? We can look at how much light is coming out and what colors are coming out, and be able to use that to infer what the temperature of these objects are that are millions and millions of light years away. It's also how these, we're all now used to these non-contact thermometers, unfortunately, these days. And that's what's happening too. So when you're getting scanned before you go to school or whatever to make sure that you're not sick, what this infrared thermometer is doing is it's taking a spectrum, essentially, of your forehead and figuring out what your temperature is based on the very same physics, the very same mathematics that we use to figure out how hot the surface of our sun is. Right? So by knowing where this peak wavelength is, we can figure out the star's temperature. By figuring out all the colors of light that are here, we can figure out how much energy the sun is putting out. But that's not the only thing that we can do with light. We can also take what's called a spectrum. And so at the library right now, I just dropped these things off, are one, a bunch of really cool diffraction pattern glasses. What these glasses do is they break up the white light, all the colors of light, and they separate them out in terms of angles so that we can see what's going on. I've also dropped off at the library just this afternoon and gave a brief training to all of our wonderful librarians that work there. These little spectrometers. And what these spectrometers have is they have a little piece of diffraction grating right here. And the diffraction grating is a piece of plastic with little etches in little straight lines that are etched into that diffraction grating, such there's about 600 of them per millimeter. So every space like that, they are able to etch 600 lines into that. And what that does is it causes the light to start to bend in different ways. And on top of that, we got so many cameras right here. I've dropped off a couple of different lights. And so what I've got here is a helium. And you can see it's kind of glowing. I don't find it to be a very pretty color, to be honest. I gave the librarians all my nice ones. We have hydrogen at the library, which is my all-time favorite color because it's this really, really beautiful bright pink color. And I gave neon, which is a really strong blue color. And so now what I got is I got another camera. There we go. And so actually, let's stop the share so you can see a little better. And so what I'm doing is I'm taking my spectrometer and I have a little webcam associated with this thing, and we're looking right through that spectrometer, and we can see that this color, it's upside down, that's interesting, that the helium is putting out a really bright yellow line and kind of a magenta line over here, and then it's a green and some blue. And if I change the tube, you can put mercury. You can see that the spectrum has changed. So every element has a different chemical fingerprint associated with it, right? And that chemical fingerprint is told by the colors of light that we've got right over here. Turn that off because it makes a really, really annoying buzzing sound. And those are for you to look at the library. So if you want to take a look, there's a handout over there. You have these spectrometers that you can use to look at, and then you can also take home these really kind of fun glasses as well. And so what we've got here is a picture of using our regular telescope, and each of these lines across here is a spectrum that's going across here and looking at each one of these stars. And it's a little hard to see in here, but you can see the lines show up a little bit differently. And what this allows us to do is it allows scientists to figure out what elements, what are stars made out of. And we find that young stars starting out in their life are primarily made up of hydrogen with a little bit of helium and a few other things that are going on in there. And as the star ages, it burns up a lot of this hydrogen, or it uses up a lot of this hydrogen. It's not really a burning thing, but you know, we say that. It uses up all the hydrogen and converts it to helium. And then all of a sudden in the spectrum of those stars, you start to see some helium. Then that helium starts to run out and it starts to smush the helium together to make carbon and oxygen and things like that. And by looking at these spectra over here, we can figure out what is coming out of the stars. And so you might have heard the phrase, you might have heard somebody say, we are all made of stardust. And while maybe we're not made out of stardust, we are made out of stars. When the universe was created roughly 13.7 billion years ago, most of the elements that were out there was hydrogen. And there was this like 99.9% hydrogen or something like that, a small little skosh of helium, an even smaller skosh of lithium, and that's it. And we're made out of carbon, and we breathe oxygen, and we have magnets and things like that. I'm made out of aluminum and iron and all that. And all of the elements up through iron came from the very first stars that were ever born. And these were giant, giant stars. And they used up their fuel so fast that when they exploded at the end of their life, they just spewed out all of the periodic table. And so inside the stars, you can make up to iron. And then you say, well, that's only about half the periodic table. What about the rest of the periodic table? Well, the rest of the periodic table came when the stars actually blew up. All of the stuff is flying out at super very high speeds, and they're all colliding with other things. And when they're colliding with other things, they made all the heavier elements. So with the exception of hydrogen and a little bit of helium, most of all of the other elements in the periodic table were generated from stars. And we know this in part because we are taking these spectra. And each element, each molecule has its own little light fingerprint. And so we can use spectrometers to be able to figure out what that fingerprint is. That is what we're going to be using on James Webb as well. And so here's another little picture that kind of shows you it's a little bit better than my webcam, I admit. So, you know, if I all of a sudden I see, oh, here's one red line and an orange line and a blue line and a violet line, then I might say, oh, yeah, that's lithium. Right? And if I see a little bit more complicated spectrum like this will be calcium. And sodium, those are like those, we don't have those in Oneonta anymore, but those weird orangey lights, street lights that made everybody look kind of sickly, those are made out of sodium lamp. And so that predominantly is this orangish yellow line right over here. And so we can look at this and figure out what's going on. Now, the really other thing that's really interesting is we can use this fingerprint and also to figure out how fast things are going. Because maybe you've heard of the Doppler effect, right? And so you might have heard about it with like an ambulance, right? So as an ambulance is moving towards us, the pitch of the siren sounds higher and higher, higher pitch. And then as the ambulance moves past us and moving away from us, this pitch of the siren starts to sound lower and lower frequencies. And the same thing happens with light. And so if all of a sudden we see a lithium spectrum like this, but it's all shifted over to the blue, we know that whatever it is coming right at us. And if it's shifted over to the red, then we know it's moving away from us. And we can figure out not only that it's moving towards us or away from us, but we can use it to figure out how fast it's going. And so maybe you've heard about this mysterious thing called dark matter, right? That there's most of the matter in the universe seems to be stuff that we don't know what it is, that it doesn't actually glow. You say, well, how do we know that? And so if you remember this picture from way back at the very beginning, this galaxy, these arms are spiraling around like this. And so sometimes if the galaxy is kind of on edge towards us, then one part of the arm will be coming towards us, towards you, and one of them will be coming away from you. And so stars on this side might look blue shifted, and this side over here red shifted. And so they can figure out how fast these things are moving around like this. And then when they figure out how fast those stars are rotating around the galaxy, and then you do some math that I just taught my students how to do in their introductory physics class, you say, wait a second, there's not enough mass in the galaxy to make it spin like that. So what's going on? And so we have to infer, there's a couple of other things too as well that scientists don't ever like one piece of evidence. We like to get like 3 or 4 before we feel comfortable saying that something exists. But there's one piece of information. And again, it's all coming from these really cool properties of light. And so that brings us then, so what is going to be so special about the James Webb Space Telescope? So what I got here is a picture on the left is a drawing of what the James Webb Space Telescope is going to look like. And on the right here is a picture of the Hubble Space Telescope that's been working for so many years to provide such beautiful pictures. To give you a sense of scale, the Hubble Space Telescope there on the right is about the size of a school bus. And so the James Webb Space Telescope is about the same, although it weighs about half as much. And that's because if it was going to weigh as big as much as the Space Telescope, we would need a lot bigger rockets than we have. And we're using the biggest rocket that exists to be able to launch this thing out into space. So first of all, we can see a couple of things here. We can see that the James Webb, that the Hubble telescope is about 8 feet wide. And the Hubble Space Telescope is about 21 feet wide. And so that is much, much, much bigger. So that means that the James Webb Space Telescope is going to be able to collect 6 times more light. So it's going to be able to find things that are way, way, way fainter than Hubble ever could. And Hubble is one of our best telescopes that we ever had. The other thing that's really interesting to notice here is that this looks like a beehive almost, right? It's got this honeycomb structure. And the reason for that is because this 21-foot mirror would not fit into any of our rockets. And so you might see it's all folds up like an origami thing. And in fact, they used origami techniques to try to figure out how this thing is going to work. And so it's going to get all shoved inside this space capsule. And when it finally gets out into space, it's going to open up and the whole thing is going to have to unfold like a flower. And so the idea is to make a big telescope mirror out of a bunch of smaller ones. To give you a sense of scale, this thing is about the size of a tennis court. And so here are the mirrors. And then you might be asking yourself, what is this thing down here? What is this? Well, on the underside are solar panels. So what's going to happen is that this whole thing is going to be tilted away from the sun. We'll get back to that a little bit. And the solar panels are going to help power the James Webb Space Telescope. But these sails here are also going to keep the James Webb Space Telescope cool, right? Because we're going to be looking at the infrared, and the sun does put out a ton of infrared. And so we got to block that out. Otherwise, you wouldn't even be looking at the sun, and the sun would be putting out so much energy, it would easily overwhelm James Webb. And so this thing is going to be out. So the Hubble Space Telescope is about 570 kilometers above the Earth's surface. This is not to scale. The moon is about 384,000 kilometers away from the Earth. But even if we put the space telescope that far away, it would still be overwhelmed by the sun's heat. And so we're going to put, scientists are going to put this thing 1.5 million kilometers away, about 900,000 miles away at a special point in space called the Lagrange 2 point, or L2 point. It's a special point where everything is pretty stable over there. The Earth going around the sun, the other planets aren't going to disturb this thing, the telescope very much. It's going to be able to sit in one place without having to fire rockets to keep it in one place. It'll stay in just space right where it's supposed to. And so only by putting it that far away will we be able to keep things cool enough. And so what are we going to be able to do? Well, light travels at roughly 186,000 miles every second. Okay, 186,000. The circumference of the Earth is only about 22,000 miles. From one side of the United States to the other is about 3,500 miles, right? So it is like literally moves in the blink of an eye. But even then, space is really, really, really big. And so the sun is the closest star, obviously, to the Earth at 93 million miles away. And so the light that comes to us from the sun left the sun 8 minutes ago. It takes light, even as fast as it is, it takes light 8 minutes to get from the sun to us. And so the further away something is, then that means that we're actually looking backwards into time. So the next closest star to Earth is called Sirius, and it is 4.7 light years away. So that means that it took, when we look at that star at night, the light that's coming from us took over 4 years to get here. You look even further away, you look at some of the other galaxies that I showed you earlier on in this talk, those are something like a few 100,000 light years away. So the light that's coming to us now left when we were just starting to become Homo sapiens. right? And I always think that's kind of cool. And so we can look way, 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 way back. And so Hubble was sensitive enough to be able to see the back in time about, what did I say, about 12 billion years ago. So about 1 billion, almost 2 billion years after the universe began. And at that 2 billion years after the universe began, that is roughly when galaxies first started to form, when all of the stars that had been around start to get gravitationally attracted to one another and form those beautiful kind of pinwheels that we see. James Webb, on the other hand, is going to be able to go back far enough in time to see the first stars that were ever created. Right? They no longer exist, but it's taken light so long to get to us that we'll be able to see those things. Just imagine that. If this thing works, then we're going to be able to see the very first stars. In fact, we're hoping that what we can do is we can look back to the very earliest times of the universe, which is called the first reionization event. There was a time where it was just this crazy soup of subatomic particles all interacting that light couldn't even get anywhere. It was just always scattering. And eventually things cooled down enough that atoms are first able to form, and then light was able to escape. And we think that we might be able to get back to that very earliest part of the universe, which happened about 400,000 years after the Big Bang. Right? And so we're going to be able to look back in time and be able to understand that. But we're also going to have these spectrometers. And so we know, we've just been discovering that so many stars in our galaxy and other places have planets that are going around them. And we would like to know, do those planets have atmospheres like Earth? And so what we can do is, what's going to happen is that these planets go in front of their stars. And we might not be able to see them directly, but as the light from the star goes through and passes through the atmosphere, it's going to get absorbed. And so we're going to be able to find a spectrum that's going to be in the infrared. And so if we see a big dip in the spectrum of the star right here at 16 microns, we know that there's going to be a lot of carbon dioxide in that planet's atmosphere. We might be able to see if there's water in the atmosphere. We might be able to see if there's methane and things like that. And so one of the hopes is that we're going to be able to look at what these exoplanets are atmospheres look like. We're also going to be able to look at the planets closer to home, and we're going to be able to find out, look at the rings of Saturn. We're going to be able to look at the oceans of Ganymede. It's a frozen planet. So it's all covered in ice, but we think that there are liquid oceans underneath that. And so we're going to be able to look at that using James Webb Space Telescope. So those are some of the really, really cool things. And then some other ideas. I just wanted to kind of show you what this thing is going to look like, right? So we got this sun shield. And so the light's going to come along here. It's going to get reflected on this first mirror, but then there's going to be a second mirror that it all gets focused onto, and then onto all the different kinds of cameras and spectrometers that exist on the backside of the James Webb Telescope. The sun will be down here. And that's what it looks like in the lab before they folded it all up. And like I said, the sun is going to be really hot. So even on this side of the, even though we're going to be 900,000 miles away, it's still going to be able to warm this thing up to about 125 degrees Celsius. And so those baffles here, those sails, are going to trap that heat and get it to go away off to the sides, away from that very sensitive equipment, such that on the inner side, it's going to be minus 390 degrees Fahrenheit. So on one side of this thing, and this thing is like only like maybe a foot or so deep, on one side, it's going to be hot enough to boil water. And on the other side, it's going to be negative 390 degrees Fahrenheit. And so those are some of just the cool things that I think are cool about this. And so again, at the library, for the next couple of weeks, there's going to be some handheld spectrometers that you can look at. We have a neon lamp there, we have a hydrogen lamp there, and we have a mercury lamp. And I encourage you all to take a look at these things because you can learn a lot. If you look up at the lights in the ceiling at the library, you're going to find a color spectrum like you would like a rainbow, but then you're going to see a couple like specific color lines that also kind of like jump out at you. And if you're really paying attention to what's going on in there and you look at the mercury lamp that I provided, those lines are going to be exactly the same. And so now we've just learned something about how our fluorescent lamps work. Our fluorescent lamps must have some mercury in there because we can see its fingerprint. And that explains why we have this white coating on there. So what happens is we send electricity through our fluorescent lights. It gets the mercury atoms all agitated. The mercury atoms emit that agitated energy in the form of light to become de-agitated. And then that white powder that's on the inside of those lamps absorbs some of that light from the mercury atoms and re-emits it in all of the colors to give us the visible spectrum. So anyway, enjoy those. Take home your glasses. Read a couple of cool books in the library about atoms and elements in space, and keep your eyes open for that launch in December. Have a good day, everybody.